Good morning, everyone. This is Ashutosh Gupta and Neha Sharma. Today, we will be going to present one of the recent works called as GraphTrail, translating GNN predictions to human interpretable logical rules. In recent years, GNN have achieved remarkable performance across a variety of graph structure tasks, from social network analysis to molecular predictions. This success stems from the ability to leverage both node-level features and graph topologies, learning powerful representations and making accurate predictions. However, one of the major challenges remains still, that is interpretability. The internal reasoning of a GNN is still a black box, making it difficult for domain experts to understand why a prediction was made. Our work that we are going to present today will address this interpretability gap. GraphTrail aims to translate the predictions made by a trained GNN into human interpretable logical rules. In other words, instead of training a GNN as a black box, we will extract from it a set of logical formulae that approximate or explain its decision. Neha? Neha?
Yeah.
Uh,
So as Ashutosh explained that we will be not only using the black box prediction, but we will be also using Boolean formulas. So there were earlier works on this research area of around GNN explainability, but they had certain limitations, which is they focused only on a specific snapshot of a graph and not a set of graphs or multiple data sets. So this is what we target here in this paper. This paper like this paper focuses on maintaining a global interpretability and not instance level interpretability. So because if we focus only on instance level interpretability, it leads to increased computational cost. So yeah, Ashutosh, you can continue from here.
yes, now let's go over the complete overview of the graph tail. Let me walk through the key ideas first. The first thing and the primary most thing is concept extraction via the computational trees. We analyze the GNN's computational graph on each input, capturing how relational patterns and feature propagates through the network. These form computational trees, which encapsulates a specific subgraph and feature-based computations that the GNN used for its decision. Then we calculate the Shapley value based importance scoring for each of these computational trees. For each computational tree, we compute importance score, that is safety values basically, to identify which part of the computation are most influential for the GNN output. This let us prioritize the most relevant patterns from the computation trees. Neha?
Yeah. So once we have the list of Shapley values ready, we find the top most high Shapley score values, and then we formulate those related computational trees into a Boolean logical formula. So once we have our Boolean logical formula ready, then we find the global level insights of all the graphs which we are using in our process. So this is the property which I mentioned earlier, that using these symbolic regression formulas, we find the global level graph traits of our data set rather than focusing only on instance level properties. So yeah, Ashutosh, you can continue.
Uh, so in the methodology, Neha, you were going to explain.
Yeah. Yeah. So earlier what we explained was the high level methodology briefing. Now let's dig a little deeper into it. So first we have a set of graphs of a specific use case. Suppose a chemical based data set. Once we have that, we find a computation tree of each and every node present in all the graphs. So suppose we have four graphs and each graph has around 50 nodes. So that counts to total 200 nodes. So we find total 200 nodes corresponding to each and every node of the graph. Once we have a list of computational trees ready, what we do is we perform a process of canonization. So canonization is basically finding only the unique computation trees, because once we find a computational trees, we realize that for two different computation trees, for two different subgraphs, their computation trees comes to be a same. So that is why, just to avoid redundancy, we perform canonization and then we get a list of unique computation trees which we used as an input for the GNN prediction. Once we have a GNN prediction ready, we get a C-tree embedding. As you can see here, we find the C-tree embedding of each and every computation tree, and then we form a matrix out of it, and then we have another matrix which we called as concept vector. So concept vector matrix is analogous to the adjacency matrix we have in our graph theory. So the value of 0 and 1 in the concept vector basically denotes the presence of particular computation tree in a graph. So if suppose we have a graph G1 in our data set, so all the computation trees we will search in that graph, and whatever are present we will mark it as 1, and whatever computation trees are present or absent in that particular graph we will mark it as 0. So that is the that is the process of concept vector formalization, and then we use both concept vector and C-tree embedding for the Shapley value computation.
After we obtain the unique computational trees and concepts, we still don't know which of these concepts actually influence the GNN decisions. To make these to rank them score-wise, we use the SHAP values. Shapley value is a game theoretical method that evaluates each concept by checking how much the model's prediction change when that concept is added or removed. If removing a concept consistently causes a prediction confidence to drop, it gets a high SHAP value. If the predictions stay the same, the concept is not useful. In this way, we give the fair and reliable ranking for these concepts. Now, using these concepts, we keep only the top influential concepts. Currently in the code, we are using only top 50 of these and we discard the rest. This filtering steps simplifies the explanation and ensure that we focuses only on the patterns that the GNN genuinely relies on. Once we have these concepts, we pair them up with the black box model predictions and feed them into the final stage, that is symbolic regression. Using the PYSSR library, we are able to find out which of these 50 selected ones are important, and then we get the list of the logical formulas. For example, over here, after getting the extracting the 50 important concepts, we were able to the PYSSR itself detects that these 10 of the concepts are important. So this is a concept representation that each concept represents a C tree, and that C tree in backend represents a small graph in the main graph. This idea is basically what rule involving these steps explains the complete model's prediction, basically. And after the PYSSR step, we are able to get the logical formula. Yeah.
Yeah. So, as Ashutosh told that we find the Shapley values of each and every computation tree. So, as you can see here, we performed an experiment for one of the data set. So, you can see here we found the Shapley values, and then we selected the top 10 highest Shapley values related computation trees. Then we pushed that computation trees into the symbolic regressor, which is PYSSR, and then it generated multiple formulas with their different level of complexities and their accuracies. So based on that, we selected a single formula which was like highly accurate and less complex. So as you can see here in the rule generation, we can see only one formula, which is an OR operation of computation tree number 188, 199 and 159. So that's denoted we summarized up our whole data set using these three using the boolean formula of these three computation trees with training accuracy of 0.809 and test accuracy of 60, that is basically 68%. So that is how we moved from GNN prediction to its rule generation as well. So Ashutosh?
Thank you, Neha. So this is what it is, but there are many limitations involved over here. Both the GraphTrail and its competitive GLE explainer express rules using logical formulas. However, they cannot capture how many times a concept appears in this graph. And in our novelty, we are trying to explain this multiplicity, that how many unique C trees are comes under the same, how many unique C trees comes within the same graph, within the with how in the frequency of graphs, basically. And we are able to get a bit improved result for that. Thank you.
Yeah, thank you.